So we now continue that the analog to digital converter. Now earlier, few decades back, this was required to be a separate chip, and it was actually when microprocessor was there, that time microprocessor to which some peripheral interface like 8255 or some other devices, and an ADC is a separate chip which was required to be connected to microprocessor. But now as things, especially VLSI progress was very much rapid, what happened that this analog to digital conversion technology also has grown rapidly, and then previously the analog to digital conversion means what is exact analog to digital conversion, that I will describe it slowly, but right now just I want to stress that now it is so progressed that this analog to digital converter is now included in the Arduino itself. There is no need for a separate chip to be connected. So it is part of the Arduino itself. Means microprocessor earlier and allied things, all allied things are now brought inside the chip. That is the progress what I want to stress. So let us now very briefly we can talk about analog to digital conversion. So what is done is that analog to digital converter is having one analog input. Obviously a power supply is there, a ground is there. Power supply can be 5 volt, that is not so right now important. Analog input, and so it is having one analog input pin. This is ground. So this voltage, and the voltage range is say 0 to 5 volts. Voltage range is 0 to 5 volts. So this supply normally we take it to be 5 volt, but that is not so something critical right now. That is not our botheration. So 0 to 5 volts is analog voltage. Then this analog voltage is converted into n-bit binary number. This analog voltage is converted into n-bit binary number, and what we can do is means n-bit binary number. Suppose if we select n equal to 8, then 8-bit binary is having 0 0 0 0 0 0 0 0 till 1 1 1 1 1 1 1 1. That is the minimum number in 8-bit is 0 0 hex. That this is 4 bits we call a nibble, 4 bits we call a nibble, and bit and hex. And this 1 1 1 1 1 1 1 1 is what is F in hex. So the maximum 8-bit number is FF. Maximum 8-bit number is FF. So it starts with 0, ends with FF. Then on the analog side, you have got 0 to, let us say, 5. Then you are having some kind of scaling adjustment, so that what is done is you can map 5 volt should correspond to what. So if you map here, FF in decimal is 256. This just I am telling so that computations become simpler. In fact, this simplicity in computation has become now an obsolete term because everything is now computerized, but still we are somewhat used to some simple things. So there would be a combination, called as 1 1 1 1 1 1 1 1 and 1 0 1 0. This is FA, and FA corresponds to 250. FA corresponds to 250. So you can adjust this, some kind of scaling adjustment is there, so that 5 volts is mapped to FA. So means what will happen? What is analog to digital converter? When the voltage is analog, it takes all values from, means suppose if we map on a linear scale, if we map this as 0 and this as 5 volts, then actual voltage can be taking any value. It takes continuous value. Whereas when we convert to digital, what we do is we divide this 5 volts into 250 number of steps. So something in this range is treated as 0 hex. The next is treated as 1 hex. The next is treated as 2 hex. And this last step we treat as FA hex. So what is done is, actually, if time permits, I will elaborate various ADC techniques also, because that is also a very interesting thing. But right now, with exams near, time doesn't permit us to go into details of analog to digital conversion. So in short, we can think of an analog to digital converter is having a continuous input and is having n digital outputs, where n is normally 8, or if more the n, suppose that there is I will explain 1 bit ADC. What 1 bit ADC will do? 1 bit ADC will, if I have 5 volts, then something below 2.5 I will say is low, something above 2.5 I will say is high. If I have 2 bit ADC, then something below 1.25 is low, 1.25 to 2.5 is 1 point, something below 1.25 is 00, 1.25 to 2.5 is 01, 2.5 to 3.75 is 10, 3.75 onwards till 5 is 11. So if I have got n bit ADC, then I am able to divide the entire available analog input range into 2 raised to n parts, and if voltage is there in that part, I take it as a particular level. Voltage between, next means the window size becomes 1 upon 2 raised to n, and higher resolution. The Arduino is having an ADC, you have performed experiment also, that Arduino is having 10 bit ADC. 10 bit ADC. So its maximum value is 10 decimal or 3FFH or 3FFH, and that is mapped to 5 volts, or you can have some mapping also. So if we do this 0 to 5 volts, if you suitably map such that 5 volts corresponds to, you can map to FF also. If you map to FF, then 5 volts upon 255, that is 1 upon 51 will be the volts, will be 1 step. Instead you map, instead of 255 you adjust scale such that it is 250, then it will be 1 by 50, and 1 by 50 is point not 2 volts. Point not 2 volts will mean the count of ADC will move at 1, means point not 2 is the size which would be converted, which will be mapped for one digital value. So something between 0 to point not 2 will be treated as 0. Point not 2 to point not 4 will be 01 hex. Point not 4 to point not 6, 02 hex, and so forth. So in all, from your point of view, the thing to be remembered is that there is an inbuilt ADC inside microcontroller. So the input pin is a separate input pin. Input pin is a separate input pin that is called an analog in. That is called as analog in input pin. So when you read that pin, when you perform an instruction, so everything is now inbuilt. Instruction set is wider. It's a very rich instruction set. When you read that analog input pin, in that case, whatever you get is a 10-bit value. In case of Arduino, you get a 10-bit value which will between 000 hex to 3FF hex. So that is corresponding to 5 volts. So that value you take and you can process that. So analog to digital converter, what is the biggest advantage of it is that analog to digital converter helps us or makes it possible for Arduino to read digital equivalent, means microcontroller needs digital value. The values in practice in real world are continuous or analog. So analog to digital converter interface enables microcontroller to read digital equivalent of analog voltage. This analog voltage has come from some or other kind of continuous variable, say for example temperature, pressure, its flow. There are many continuous variables, means in the real world there are many continuous variables which when we talk of industrial automation, there are many real-time variables which we need to be mapped into their digital equivalent to be read by the microcontroller or Arduino to be used for some kind of computation to generate some results. So ADC allows microcontroller to read a digital equivalent and use it for computation. So we take, using ADC, we prepare a temperature controller. See, for example. So if I want to have temperature controller, first thing what I need is there should be ADC, there should be temperature sensor which we discussed, temperature sensor output. So if I want it for water, if I want an application for water temperature controller, so temperature sensor is to be mapped. What is maximum temperature of water? Water boils at 100 degrees. So temperature sensor circuitry, that details we don't, means it would be time consuming. Say circuitry is to be adjusted such that 100 degrees will be mapping to 5 volts. 100 degrees will map to 5 volts, and that 5 volts, that my ADC will map to FA hex or 250 decimal. Means what? And 0 to 0 obviously, it's water, so it will not be below 0. Only it's water level controller, 0 volts with 0 hex. 0. Means what this will do, what whatever value I get means the temperature sensor is put in where the temperature is to be measured. Its output is connected to a circuitry that generates 0 to 5 volts, that is connected to ADC. Right now I am taking 8-bit ADC. In Arduino there is 10-bit ADC. We can go for that also, or we can go for this one also. If there is a 10-bit ADC, then I will make it to be 3. If it is 10-bit ADC, maximum range is 1023 decimal. So in that case, I will map it to be 1000. 1000, or I think that would be unnecessarily complicated. Of 10-bit, it is better to stop at 8-bit only. That it is just for giving example. So that is 250 decimal. So what does it mean? It means that whatever value I get from ADC, 100 degrees will be corresponding to 250. So I have to multiply, I have to divide. So the actual temperature is in my algorithm inside Arduino. What is my conversion formula? It is very simple. In fact, it is just once the concept is clear, it is high school level maths. We should not even spend this much time. So temperature is ADC reading divided by 2.5, or 2 into ADC reading . Right? So if ADC reads 250, temperature is 100. If ADC reads 125 decimal, 00 to F8, actually it is getting in hex. I convert to decimal for counting purpose. So if I get 125, the temperature is 50 degrees. So with what this ADC will make me to read the temperature. Now I want to control the temperature. For control the temperature, there is a heater. So like ADC, there is a counterpart called as DAC. There is a counterpart called as DAC, that is digital to analog converter. That is digital to analog converter. What the DAC does, a DAC is having n digital inputs, 1 digital output. So n digital inputs, the maximum value is 2 raised to n minus 1. So if I have n inputs as n as 8, then 255 is the maximum combination, or F hex. So, and on the analog side, there is some maximum voltage. Normally we go for 0 to 5 volts. Then FF is mapped to 5 volts. Or you can have scaling adjustment so that FA you can map to FF, you can map, or it's the best way of using the calculation simplicity is 5.1 volts. Means what? FF will be mapped to 5.1 volts, that is 255 is mapped to 5.1, so that one step means the digital input will be 255 will be mapped to 5.1. So analog output is equal to 1 upon 50 into digital input. So if digital input is 0, 0, 0, 0, 0, 0, 0, 1, then output would be 1 upon 50 or volts or 20 millivolts. This analog to digital converter will convert it into 20 millivolts. If 0, 0, 0, 0 0 0 1 0, that is the 2 hex, then ADC will convert to 40 millivolts. So sorry, DC will go to 40 millivolts, and then this can be given, means in real practice there are some systems which need continuous input. So that is generated by DAC. So ADC and DAC are essential parts if ever we want to interface real world things, with microprocessor, microcontroller, Arduino logic. In that case, ADC and DAC both are required. So in general, a microprocessor or Arduino based system will be that ADC is part of microcontroller. That is different. So on a block schematic level, ADC continuous input, DAC continuous output, and this is microcontroller. So this ADC is connected to microcontroller, it may be inside, that's not a major issue. So DAC is connected to microcontroller again. So how microcontroller gets itself interfaced with external world? It reads the actual, this is continuous variable. Normally we use in the region of 0, not necessarily, it is also continuous. So something between 0 to 5 volts is converted into, remember that when we go for ADC, we lose some information. Why? Because we approximate. So more the number of bits of ADC, less is the approximation error. The ADC error is called as quantization error. So we read the continuous variable by digitizing it or quantizing it using ADC. We process it, we generate the digital output. That digital output we give to DAC, which generates continuous output. So through ADC DAC, this interface with external world, which is continuous in nature, is managed. Now this ADC is now part of microcontroller. This ADC is part of microcontroller, but this DAC is normally not part of microcontroller. But suppose that there is one very interesting concept that I will explain to you, where there is no need of separate DAC if things are moving at a slower rate. Means, let us talk of a temperature system, and in that there is heater. In that it is water tank, and in that a heater is put. And you want to control the heater power. Means if you want temperature to be less, here it is assumed. Now there is a concept of Newton's law of cooling. So since the atmosphere temperature is less, if you want to maintain temperature at 70 degrees, if atmosphere temperature is 25 degrees, and if you want to maintain it at 70 degrees, and there is some, what we can say, system, means whether water is there, oil is there, how much, what is the size, whether it is insulating or not, everything comprises system. So if atmosphere temperature is 25 degrees centigrade, if this is to be kept at 70 degrees centigrade, then you must give some constant heat energy to this. Suppose if at other time you want to change the system and want to make it at 80 degrees centigrade, then you have to give some other different heat energy, will be more. So this you can have a dimmer stat, it is variable transformer, and you can, means maximum is 230 volts RMS. So by using dimmer stat, you can control the voltage when you control the voltage, the heat power would be, this R is fixed, V square by R. So by varying the input voltage applied to the heater by using a dimmer stat, you can change the heat energy being supplied to the your process. But heating is a slow process. Therefore, the thinkers have thought in different ways. What they said, that there is no need of having this dimmer. Means, I want to supply half energy. If I keep the heater continuously on, then the energy is full X. If I want to supply half energy, then I need to, if I make the voltage half, energy will be 1/4 because it will be square by R. So whether I need to have dimmer because that is a costly, can I avoid it? Then, so if I make the dimmer voltage half, energy will be 1/4 full energy, and I want to give 1/4 energy. Then what they think, that heating is a slow process, is having inertia. So instead of continuously supplying at 115 volt, which will give me 1/4 energy, what they say, that I will make the heater on for 1 minute and I will make it off for 3 minutes. I will make the heater on because the heating process is very slow. I will make the heater on for 1 minute and off for 3 minutes. So in 4 minutes, it was on only for 1/4 time. So 1/4 energy of full energy, heat energy was supplied. So having a heater, having a dimmer and maintaining dimmer at 115 volt and making the heater continuously on, or don't have a dimmer, directly connect heater to 230 volts, keep it on for 1 minute, put it off for 3 minutes, keep it on for 1 minute, put it off for 3 minutes. So what I ultimately get is that when I am having 1 minute on and 3 minutes off is one case, and other case is maintain 1/4 of this always. Maintain continuous 1/4. So maintain this level. So this you can continuously change, or this you can continuously vary. Then over this 4-minute window, just take a simple case, supplying at 1/4 level continuously for 4 minutes, or supplying 1 minute at full level and not supplying at all. So effect is the same. Means if instead of changing the voltage level, changing the level of continuous variable, if I keep it full for T on time, this is called as T on, and 0 for T off, then effectively what I have given, average is T on upon T on plus T off, and into 100 if I do, it is in percentage. So that is percentage duty cycle, or even if you remove percentage, what I get is average is this. So if full is 100, then if I want to supply say 17, means what I will do, I will keep it on for 1.7 minutes, off for I can have 10-minute window, off for 8.3 minutes. So by adjusting T on, if total time I fix as 10 seconds, anything you can fix. But only thing is, if it is too large, then it will not be of use. So if by considering the process, the speed of the process, here temperature is a very, what we can say, temperature is a very sluggish process. So 5 minutes, 1 minute is negligible for means is a negligible time. Negligible time in the sense that it is too large time in which some changes can occur. So you can make the 10-second on, 50-second off. So, or you can have the best way is 100-second window time, 100-second cycle. 1 second on to be actually that is not good, because 1 second to make it on and off is also, so 1000 second or 500 second, anything you can have. Say 10-second on, 490-second off. So that would be what we can have, 2%. So effectively over the total window size you give average output of that total for the total duration. Therefore there is no need for DAC. DAC is indirectly managed by changing the on time and off time of digital output itself. So a digital output pin which can be driven in on and off manner based on some logic is called as digital output pin. Is normal pin only thing is that it is managed separately. It is called as PWM, pulse width modulated digital output. So it is very easy to implement, and since the systems are slow, there is no need for DAC. So PWM is an alternative, low cost, easily implementable digital to analog converter. So the overall temperature control based system example we will take for next time. Thank you.